Welcome to homework.
In this problem, we have a bar bent into a quarter circle, and then it has a load acting into the plane here at the end. It is again cantilevered at this opposite end. I'm going to take the origin here at the center of this circle, and then I'm going to use this as my theta. So we have, what we can do, the easiest way to do this is again using vectors. So the load out here is 0, 0 minus p. Okay, so it's into the board. And the vector to that load is 0 minus r 0. And so it's just in the direction minus y. Now, a vector to an arbitrary point on this is r er, where er is the unit radial vector. Okay, so that's going to be minus cosine theta minus sine theta. Now, what we find then is if we just look at this section here, we sum so we have an internal force vector that generally will have 3 components, and an internal moment vector that will generally have 3 components. Now, if we sum forces here, we get P plus N equals 0. And now N, or P, just has a component in the vertical direction, in the z direction. So we have these two forces are 0, and then the force in the vertical direction is P. So this would be, the normal force would be this one. So that's 0. This would be one of the shear forces, and this is the other shear force. So we have a shear in one direction that's equal to the load here. Now, if we take moments about this point, we have the vector to this, the moment from this force, the moment from this force, and then the internal moment here. And that needs to sum to 0. So we get that in this term here is P times R in the I direction, in the X direction. Here we have, this is R times ER, so then we have to cross it with N, which just has this one component, and Z in the K, and then plus our internal moment vector. Now this we can write down, let's see here, I think I didn't finish going through this problem, so let's just finish it by hand here. We can write that the moment, we can write it as m equals nzre theta minus pri. Now we need to, if we take this in the components, we find it in the cylindrical coordinate components. We know that, let's see here, let's write down what E hat R is, and that's minus cosine theta minus sine theta 0. And then let's write down what E hat theta is, and let's say that is that's in this direction here, right, as theta increases. So that would be, let's see here, that would be sine theta minus cosine theta 0. So if we take m data with ER, that this gives the first term here gives us 0, and then we get minus P. Let's see here. We get minus P R, and then ER dotted with I so we get, let's see, PR cosine theta. So that's m theta. And m theta is going to be a twisting moment. So again, this load is causing a twisting moment in the beam. And let's see here if we can find a little space out here to figure out m dot e theta. Oh, sorry. So, wait, I said that wrong. This is m theta, mr. mr. And so mr, about moment about the r, the radial direction, so moment about this point is actually a bending moment. So this is going to be acting to bend the beam, and I guess it looks like I wrote RR, so this should be PR. And so this is, let's see here, we have NZ times R. NZ is P, so P times R. And then we have I times I dotted with E theta is sine, so minus PR sine theta. And that's m theta. So we have PR times 1 minus sine theta. And that is the twisting moment. Now let's see here. When theta equals 0, yeah, we just get that this is P times R, so that makes sense. When theta equals pi over 2 out here, then we get that this is 0. Alright, that makes some sense. Now, let's see here. So when theta is 0, this is also 0. And when theta is pi over 2, sorry, this is also 0. When theta is 0, this is P times R. Alright, so that makes all sense. So here, this is a bending moment, and then this is a twisting moment acting in the beam.